In this question, which is a pretty strange question because it gives you a very unique mountain-shaped graph, we are going to look at the gravitational potential between two stars, okay? So if you are struggling with the concept of gravitational potential, please watch the earlier examples where we look at the potential of one planet. One planet first, one by one object, one body first, one star first, before we do two lah, okay, one by one. But in this question, this level up question, we are actually going to look at the potential between two different stars. So star A, got star B, and then, wow, look at this potential graph. Why like that one? What is going on? Okay, this is actually a really tricky concept because it's very abstract. It's the first time you hear the word potential. And to be honest, when it comes to English, potential is just something nice to write on someone's testimonial, right? Students show great potential to be a great scientist, you know, that kind of thing. So what is potential? And we will encounter the idea of potential again in electric field. So if you understand this, your electric field will be easier. If you don't understand this, you can understand in electric field first, because electric field, we will pay more attention to potential because electric potential difference is more familiar to you, yes? Okay? And then you can circle back and look at this, okay? But for gravitational potential, very seldom we encounter two bodies. Normally, we only got one. Okay, this one got two, okay? Okay, so I will read the question first. So this question, it says, by reference to the definition of gravitational potential, explain why gravitational potential is a negative quantity. Okay, so they're asking you, why is potential always negative? Okay, so I'm going to draw out the potential graph for you. Okay, very quickly. So let's say this is an object or a planet or a sun. It doesn't really matter. Okay, and this is m. All right, so gravitational potential is given by the equation negative gm over r. The graph will look like this. Of course, it touches the axis at infinity because this is potential against distance. Okay, so let's say you have a random mass here at infinity. Okay, so there will be more details about this in the lecture videos. But let's say you have a mass here at infinity. At infinity, right, the field does not touch the mass. That means the mass is just chilling lah, bro. I'm chilling. So I say this is M1. M1 is just chilling there, minding his own business. Until someone or some scientist decides to say, hey, M1, I need you to move here, bro. You just gotta move here for me. Thanks. So if you want to bring M1 to M2, somebody has to do the work. And in this case, this sun or this planet be like, me. I help you. I help you, M1, to move from infinity to this point. I help to move from infinity to a distance of r. So when you're going to measure r, we will measure from the center to here. Here to here, because this is 0 ma, so this is r. Okay, maybe this one, if this 2r confuses you, then you can take this one as x. X is distance measured from the center of the sun. So science is like, I am very happy to bring m1 from infinity to here. So this means, number one, a few things that you will notice. Number one, gravity is always attractive. So it's always very willing to bring a mass from infinity to a point. So work is done by gravity or gravitational field to bring the mass, bring a unit mass from infinity to a point in the gravitational field. So this point is at r lah. So because gravitational field is always attractive, let me change this, not gravitational constant, gravitational field is always attractive, point number one. And point number two, work is done by the gravitational field to bring the unit mass from infinity to a point. And because work is done by the gravitational field, I can say that, I can use this term called work got out. You do work already, right? So work got out. I personally don't like to use this word because I feel weird. I didn't learn it that way. but apparently Cambridge allows it. So, okay, we can say work got out because gravitational field do the work ma. So when they do the work went out. If it fits in your headline. It does not fit in mine. I don't know why this one keeps changing. Hang on. Okay. So if work got out, then what I can say is hence GPE decreases. But GPE at infinity is 0. How do I know GPE at infinity is 0? Because at infinity is very far away. The field is not acting. So if the field is not acting, there's no gravitational potential energy. So if it decreases from 0, GPE is always negative. So you imagine the place with the largest GPE is at infinity. But infinity is already 0. And whenever you bring something from 0, you have to pay energy because gravity is doing the work ma. So gravity is say, come, I do the work. So when gravity do work, gravitational potential energy decrease. It's just like when you drop something from higher ground, from further away from the center of the earth, when you drop something, the GPE will decrease. So if this M1 move to the center, GPE decrease. And when GPE decrease and you decrease from 0, GPE will always be negative. This is the full explanation if you don't want to memorize. Okay, so the whole idea is, number 1, gravity is always attractive. You bring something closer, you are decreasing the GPE. Since at infinity, GPE is 0, you decrease from 0, negative. Anything that's less than 0 is negative. So the main points that you should mention here is gravitational potential. Let me adjust the size to make sure it's correct. Okay, gravitational potential at infinity is 0. It's defined as 0. Since gravitational field is always attractive. Now I'm going to write what makes sense to my brain, okay, to help it. Since gravitational field is always attractive, work is done by gravity to bring an object from infinity. Hence, gravitational potential is negative. Okay, keywords. Gravitational potential at infinity is defined as 0. Since gravitational field is attractive, work is done by gravity to bring an object from infinity. Because this is the definition of gravitational potential, which is gravitational potential, the sign is phi. Phi is work done per unit mass in bringing an object from infinity to a point. In bringing work done per unit mass, in bringing an object from infinity, because we like 0 to a point in the gravitational field. So please be familiar with the terms. Take some time to go and brain why is it always negative. So basically what we are trying to tell you is, let's say I have an object on the surface of the earth, maybe a stone. One day I got very fed up already. I want to throw the stone away. I don't want the stone to come back. I want to launch the stone far away. I just want to throw it away. I'm throwing the stone away, assuming that there's nothing else around me to help attract the stone. I actually need to bring the stone from this point, this negative energy depth. You owe the planet or the sun this much energy, and I need to give it enough kinetic energy to shoot out to infinity. It's a bit like I have a ball here, and I need to give the ball a kick so that it can roll up until the plane is horizontal or flat, which is at infinity. So I need to repay this much energy per unit mass depth. You owe the Earth energy. Once upon a time when the solar system was formed, gravity did the work to pull all your molecules together and put on this planet. You want to run away from the planet? Can. Pay back the energy debt. Right? Which is essentially what this second part of the question is talking about. Here now we have two stars. Now when you have two stars, the situation changes a bit because star B is like, hey, you want to escape from star A? Can. I'll help you. You just need to travel to a point where my field is stronger than star A's field, and then I can just bring you over. Okay, no, sure. So now we have star A and star B. Let's look at what happens between them. They are separated by a distance of 1.4 times 10 power 12 meter. Okay, sure. Point P lies on the line joining the centers of the two stars. The distance x of point P may be varied. Okay, so basically I am measuring the work done per unit mass, every single point along this line. Okay, so the variation with distance x of gravitational potential at point P is shown, and it looks like this. Okay, so what I'm saying is star A is here, or at least the center of star A is here. Okay, the center of mass of star A is here. And star B, hey, no, wait, this is 1.4. So we measure x from the surface. So this is the surface of star A. Okay, no matter. This x from the surface of star A. Okay, so we're measuring from surface to surface. Okay, sure, no problem. So star A is here. Okay, and star B is here. I'm not sure which one has more mass, or rather I can actually tell from the graph one, but never mind first. So first things first, we gotta identify whether this set face, whether this graph makes sense or not. Okay, number one, what this graph tells you is the summation of both energies. Okay, so let's consider the potential graph for A and the potential graph for B. So let's look at A. For A, the potential graph, just a rough sketch, will look like this. And then for B, again, don't know where B is, somewhere here lah. So the potential graph for B will look like this. If you add these two graphs together, you'll probably get a shape that looks something like this. Does that make sense? Okay lah, maybe not here. Hang on, let me draw properly. So this one is a small red number, negative, plus a large negative number for blue. You get a slightly larger one. This one you get double, so somewhere here. This one you get slightly larger. So graph you're going to get is something like this lah. So let me label for you. This is potential of A, and then this is potential of B. And this purple graph is potential of A plus potential of B. Okay, so I just take a few points only. I take this point, small negative plus big negative got slightly bigger negative. These two number is intersect because it's the, I'm not sure whether this is the turning point, but it should be close to the turning point. So here is where they intersect, so I just double lah. Okay, and then this one, again, not sure that it's a turning point now. I have to calculate one, but not important. This point plus this point, I will get this point. Okay, so I'm just adding up the graph to get this shape. So this explains why you have this shape, which kind of makes sense. What? Okay, where do we know what will happen? Well, it depends. If let's say I take a 1 kg rock and I put here, it's a bit like putting a trolley here. If I put the rock here, this one will roll down to the surface of A. If I put the rock here, it will roll down to the surface of B. Meaning, this line is your line, the line where P is, ma. So if your P is here, it will be attracted to B. If your P is here, it will be attracted to A. Miss, what about this point here? At this point, it is not attracted anywhere because the gravitational attraction of A will be equal to the gravitational attraction of B, and then they will cancel out. So this is why we draw the graph this way, because it can actually help you visualize where the mass will go. Okay, so I'm gonna rub all this because it's not very important. I'm gonna read the question now. So we interpreted the graph. I'm gonna try the question now. A rock of mass 180 kg moves along the line joining the center. Using the data of the figure 1.2, calculate the change in kinetic energy of the rock when it moves from 0.1 to 1.2. State whether the change is an increase or a decrease. This is a pretty good question. I'm going to steal the graph from the website to get a clearer one, or hope to get a clearer one. Okay, so I have the graph down here for easy reference, right? We are going to move it from 0.1 to 1.2. Okay, 0.1 is here. 1.2 is here. Okay, so you just imagine you have a trolley, a 180 kg trolley, but a trolley nonetheless. You're going to move it up the hill and down the hill. What is the change in kinetic energy? Means I don't have to care about the up, down. I just need to think about the change. You are right. We just need to care about the change. So you can see that this one is the initial potential and this is the final potential. Okay, so whenever there's a change in kinetic energy, let's say you imagine a trolley moving from this point to this point, I expect the KE to increase one because it is below the original position. So you imagine a trolley sliding from the initial to the final position, will cause it to gain kinetic energy. In the perspective of the star, when I'm escaping star A, I will slow down until this point where the field of B is strong now. Then B will attract the rock towards star B and it will accelerate and travel faster and faster, faster and faster, faster and faster, faster and faster. Okay, that's why here it will slow down because star A's field is stronger. Slow down, and then after that, stop or not, I don't know. Okay, not sure, but I know it will slow down, and then at this point onwards, it will speed up because B is now the dominant field because we are traveling away from A. So I definitely expect an increase. So the first thing, whenever you see a change in kinetic energy, this is due to the change in gravitational potential energy. Let me zoom in a bit. Okay, one thing about potential that you should know is this is GPE per unit mass. So to find the change in GPE, I will take mass multiplied by the change in potential. Whenever they give you a graph, it is chef kiss perfect. Can just read. So I'm going to write M change in potential here. I know why it's M, 180 kg. That's the object that is being moved. I can deal with it later. I will take the final potential minus the initial potential. Okay, so initial is this one, final is this one. Okay, we can substitute 180. Final is how many? Negative 14. Initial is negative 10. So negative 14 minus negative 10. You wait. You see here the 10 to the power of 8. There's no way in this world where you can actually only need 14 and 10 joule of energy, okay? We are talking about planets. So we need a prefix. So I'm just gonna put the prefix at the back. Okay, so actually what I have here is 180 minus 4 times 10 to the power of 8. So I think I've done enough calculation using the digital calculator. I'm going to save my time to use the real calculator. And this one will be 7.2 times 10 to the power of 10 joule. But there's a negative here. Now, before you panic in the disco with the negative, don't panic first. You ask yourself, does it make sense? I am looking for a change in GPE. everything on this side of the equation is change in GPE. This negative shows me GPE decrease. If GPE decrease, what do you think happens to the KE? KE will increase. GPE decrease, KE increases. So the change here will be 7.2 times 10 to the power of 10 joule, and it is an increase. Okay? It will be increase because of this. So normally, the kind of question that they will ask you, if they give you a graph, it's a bonus level. Okay, so this is increase. So 3 marks. 1 mark is when I see M change in potential. This is C1. You substitute correctly and you get this one is A1, and then this one you write increase is another 1 mark. Okay, so this, if let's say this working makes you uncomfortable, you can just find the change in GPE. And then you write another statement here. You can say, well, why GME here? GPE. So what I can say is, since GPE decreases, KE increases. I mean, you write in full sentences lah. Okay? So what causes a change in kinetic energy? Because there's a change in potential energy. It's like dropping something down from a elevated height. Okay, and if you've done any AS question, you will know when it comes to this kind of roller coaster question, the actual change in height is the only thing that matters. Only here to here, the change in potential matters. How high you go, you also still come back, so it doesn't matter. Just look for the change. Okay, so this is what we mean by finding a change in GPE. In a negative here shows you that the GPE decreases. Okay, negative here shows you GPE decreases, and GPE decreases means KE increases. The reason why we are thankful for the graph is because we don't have to calculate these values. Later, I will record an example where the graph is not given and you have to calculate the values. Okay, so just take the initial point and the final point. You can treat it like you just pretend this is a trolley question. Oh, trolley, go up the track, go down the track. What is the speed at this point? You just find the height difference. Okay, so that's it for this part. Let's move on to the next one. Part 2. At the point where x is equal to 0.1, so we're back to the initial position. The speed of the rock is v. Okay, determine the minimum speed v such that the rock can reach the final position. Oh, remember how I said I don't know whether the rock is 0 speed here? This turning, is this, wait, where's the turning point? I have that meme face. Where's the turning point, guys? I think the turning point, okay, I don't know where's the turning point. Let's see, here, maybe here? Okay, let's say it's this point now, okay? So this point is the turning point, all right? So I'm not sure whether the speed is 0 here. Because when we travel from here to here, the speed decreases. KE decrease because GPE increase. How I know GPE increase? Nah, you see, we went from negative 10 to negative 4.4. 4.4. This one. So negative 10 to negative 4.4 is an increase. Right? You know, negative 10 is smaller than 4.4. Okay, because this is scalar, okay? So when it comes to scalar, the negative tells you about magnitude. All right, so this one, the GPE increase. You're moving up the incline now, okay? So basically, if you're thinking about it, I just need to send the 180 kg from this point, which is your 0.1, all the way to this point, and after that, I don't have to do anything already. After that, guess who will pop in to help me? Star B will say, okay, as long as you can bring yourself to this position at the turning point, after this, I will take over, say Star B. I will attract, you don't have to do anything, you just chill and relax. So from here to here, velocity will increase and KE will increase. And how do I know KE increase? Because the GPE decreases. It went from negative 4.4 to negative 14, okay? Big decrease. Of course, the net change is still a decrease. So right now, if I want to bring my object from this point to this point, I just need to be able to tackle this change in potential. From negative 4.4, sorry, from negative 10 to negative 4.4. As long as I can increase it to negative 4.4, this point, after that, star B will take over and attract the mass over. So I got to repeat the calculation. The only difference is my change in potential is now from negative 10 to negative 4.4. Let's go. Okay. I just need to bring it close enough to B. B will take over and attract. So I can say for minimum velocity or minimum speed, okay, the change in potential will be, I forgot the number. Okay, come. Negative 10, 4.4. So I can just take magnitude, okay? So 10 minus 4.4. Because I know it's a decrease already. I mean, I know it's an increase already, so I can take the big number minus the small one. Or you can still stay true to the sign, that is also okay. Joule per kg. Okay, means this rock or mass is what? 180. The mass is IDK. And also, I don't know and I don't need to know. Okay, so for minimum speed, the change in potential is this much. Okay, because I just need to travel. This one is at this point. The V is 0. Meaning I just need to have enough energy to reach this point. If I can run until here and then I run out of all the energy, it's okay. You got yourself there. Gravity for B will do the rest. So you just need to get yourself here. Come here. It's a bit like if you watch the lecture video before class and watch some example, then your brain should be able to digest and bring you straight to good result. But you gotta come here. You gotta come here. Okay. So come here, and then here V is 0 for minimum speed. Okay, the final speed is 0. Okay, so from here I can say the change in KE is still equal to the change in GPE, but now I'm looking at this point, 0.1 to this point. Okay lah, to make my life easier, I'm gonna find this value. This is 0.52. This point here, 0.52, right? Okay, so this one is R is equal to 0.1 times 10 to the power 12 to R is equal to 0. Hey, sorry, they didn't use R, they use X. Fine. X is equal to this, to X is equal to 0.52 times 10 to the power 12. You're not going to use these numbers. I'm just writing it here to make it clearer for you. Okay. So again, we're just going to move from here, 0.1 to the turning point here, 0.52. Okay, somewhere here is 1.2 and we don't care. All right, so kinetic energy is half mv square minus half, let's say I think v1 minus v2 square. Okay, hang on, mv2 square. Zoom in a bit. Okay, this will be m, change in potential. The mass can all cancel out because it's the same object. Okay, and also at the same time, this V2 is 0 because again, here V2 is 0. All right, so I can just take half V1 or V square will be equal to change in potential. So V square will be 2 change in potential, and I can substitute law. What is my change in potential? 10 minus 4.4 times 10 to the power, why did I put negative 8 here? Sorry, 10 to the power of 8. Yes. Don't forget your square. Don't forget the square. All right. So from here, you should be able to press your calculator and arrive at V as 3.3 times 10 to the power of 4 meter per second. So we don't need the mass. Very much like your AS questions, whenever you do conservation of energy, especially between kinetic and potential, the mass will cancel out because it's the same object. Okay, it's purposely like that one. Physics is beautiful. So in a nutshell, if you want to find minimum speed, I just need to get it to the turning point. After that, the gravity of the other field will take over. And to get it to a turning point, I only need to bring it from -10 to -4.4 times 10 to the power of 8. So then I can take the change in GP, which is mass times change in potential, and equate it to half mv square minus half mu square. But thankfully, the mass, if they want minimum speed, the velocity here is 0. So this whole kinetic energy will be 0. And what you have left is half mv square. But the mass and the mass will cancel out because it's the same object one. So you have half v square is equal to change in potential, and then the rest is just substitution. Okay, so don't forget to square root, don't forget to prefix, these are standard stuff. So hopefully this example, you really understand what is going on with this particle, okay? As anything travels away, this graph gives us a lot of information. It gives us information about the changes in energy, the changes in speed, and it also tells us if, let's say, I want to travel from star A to star B, I don't really need to have enough fuel in my rocket to go to B. I just need enough fuel in my rocket to go to this 0.52 times 10 power 12 meter. After that, star A's gravity will take over, okay? So this is about being prudent. All right, so this is a little bit like rocket science. So if you find it a bit confusing, take some time to watch through the example. Okay, that's it for this question about gravitational field and gravitational potential between two stars. I'll see you in the next one. Bye-bye.